Hey guys, in this lesson we're finally going to get around to proving trig equations, or verifying trig identities. We'll start by listing out a few general guidelines, and these will just help you through the problems anytime you get stuck. And then we'll walk through just a whole bunch of different examples. So let's get started. Oftentimes when we're proving trig equations, there'll be a point where we get stuck and we're not sure where to go next. So these general guidelines are just things that you can keep referring back to that will help you along the way. The first one though is actually a little bit more of a rule than a guideline. It says work on just one side of the equation, and you have to do that. The reason why is because the goal is to match up both sides of these equations. And by keeping one side constant and not touching it, you're making sure that you're actually proving the right thing. It will also help to keep you focused because you'll have the same goal in mind the entire time. You'll be trying to get one side of the equation to match the other. The next guideline is just a reminder of all the things that we've done in previous problems. So it says look for opportunities to factor, add fractions, square a binomial, that would be if you had like 1 plus cosine and you squared it, or create a monomial denominator. So if you have something like 1 minus cosine squared in the denominator of a fraction, you could change that into sine squared using a Pythagorean identity, and that would help you simplify, make it a monomial denominator. And in almost every step in these problems, we're going to be using fundamental identities. These are just all the identities that we've learned so far, so make sure that you have them written out somewhere and on hand. The fourth guideline is just kind of a foolproof method. If you're really stuck and you have no idea what to do, try converting everything into just sine and cosine. This is especially true if you have a whole bunch of different trig functions in one equation. Changing them all into sine and cosine will simplify things. And this last one sounds kind of silly, but honestly, don't just sit there. If you're stuck, try something. Being stuck and just staring at the problem obviously won't get you anywhere, but just look at your identity sheet and try something. See if there's something you can substitute. Just see if there's anything that you can change about the equation to get you one step further. So let's look at some examples and see how we can put these guidelines to use. So here the directions say use trigonometric identities to transform one side of the equation into the other, which is another way of saying verify the trig identity, which is another way of saying prove this. So sometimes the directions will change, but they all mean the same thing. So in number one, if my goal is to transform one side of the equation into the other, I think obviously I want to transform the left side into the right side, because the left side is a more complicated thing and that'll give me something to work with, and I want to simplify that down to just being 1. So let's see what I can do with these. I've got tangent times cotangent, and there's no identity that multiply those together and tells me what that is. So what I'm actually going to do is change tangent into sine over cosine, and cotangent is cosine over sine. So I've already technically used my first identities. These are the quotient identities. So in every step of your proof, you should be able to describe what you did. In other words, you don't want to make too many changes in one step of an equation. You can only use like one identity at a time. And since I'm only allowed to work on one side, I'm just going to write equals, and I'm actually just going to leave this blank. By doing that, that will remind me that I can't like add or subtract anything over to the other side. I just have to leave that completely alone and just work on the left side. And you've probably already seen that since I have sine over cosine times cosine over sine, everything here can cancel. And that would of course just leave me with 1, and that equals 1. In the very last step, I do write both sides of the equation. And sometimes in textbooks, you'll see like a little square at the end, and that's kind of like a period for the end of a proof. Other times you'll see the letters Q, E, D, which is just an abbreviation for some Latin expression that basically means we're done with the proof. So this stuff isn't super important, but I just want to make you aware of it. But I want to use this example to make a point about something because this is such an easy proof, and honestly when I look at it, since I've proved so many things, I see tangent times cotangent, and I know that those are reciprocals of each other, and I know that when you multiply reciprocals together, they just cancel out and they make 1. But the goal when proving something is to make it very clear what you're doing in each step. So for instance, if I just gave you this equation, tangent times cotangent equals 1, and then I just said, well, these cancel out and make 1, that might not be clear to everyone. Or in other words, someone might be able to ask, well, why do they cancel out and just make 1? So you can't skip steps. You have to show why they would cancel out and just make 1. And the reason why is because I can use this trig identity that we already know. You can use those identities as facts, and they'll help you prove these equations. So we know tangent is sine over cosine, and we know that cotangent is cosine over sine. And then this was just an algebraic step that canceled all those terms out, and we were left with 1. And then you get to the end of the proof, and this statement is so obvious that you can't argue that. 1 obviously equals 1. Now, not all proofs will end with 1 equals 1, but they do have to end with something equaling itself. Alright, so let's move on to number 2. We've got 1 plus cosine times 1 minus cosine equals sine squared. And the first thing I really have to do is decide what side am I going to work on. Now, sine squared has a higher power, so maybe you'd think that that's the more complicated side, but I'm going to choose to work on the left side just because I know what I can do here. Like, here's two binomials being multiplied together. I can just FOIL those together. Like, I have a clear idea of what to do. On the right side, I just have sine squared, and that doesn't really give me any direction. So I'll work on the left side, and I'm going to leave the right side completely alone. I'm not even going to write anything over there. Now, I recognize that 1 plus cosine times 1 minus cosine, those are conjugates, and when you multiply conjugates together, you get a nice result. But I'm not going to skip any steps, because again, when you prove things, you need to be really explicit step by step. So 1 times 1 is 1, 1 times negative cosine is minus cosine, cosine times 1, and then cosine times negative cosine would be minus cosine squared of theta. And remember, I'm not writing anything on the right side. So now we have negative cosine and positive cosine, and those cancel, so I'm doing that in a separate step, and I'd be left with 1 minus cosine squared. And now I can use a trig identity. 1 minus cosine squared is a Pythagorean identity, and that's the same thing as sine squared. And of course, sine squared equals sine squared. So in this example, we didn't have 1 equals 1 at the end, we ended up with sine squared equals sine squared. Again, I'm going to write this little square at the end just to signify that we are completely done with this proof. Now we're starting with some fairly easy proofs. There's only a couple steps involved, so they're going pretty fast, but they will get progressively harder as we go. In number 3, we have cotangent squared times 1 plus tangent squared, but we actually need to change the cotangent into cosine squared. I went through this earlier with cotangent, and it actually didn't work out, so I think this is just a typo. So what I'm going to do here is I'm going to leave the cosine squared alone because there's really not much to do, and I'm going to take this 1 plus tangent squared, and I'm going to use a Pythagorean identity, so that would be the same thing as secant squared. Again, just leave the right side alone. And then I noticed that cosine and secant are reciprocals, right? So I'm going to leave the cosine squared alone, but change secant into 1 over cosine. So of course you can think of this as being over 1, and then everything would just cancel out. And again, we're just left with 1. So 1 equals 1, and that's the end. Now, number 4 looks like it's kind of a mess. We have 4 different trig functions. We've got cosecant, cosine, sine, and tangent. So one thing I'm thinking is at some point I'm probably going to want to change everything into just sines and cosines. Another thing I noticed about this problem, thinking about like the bigger structure of it, is just that we have a fraction minus another fraction. So in order to add or subtract fractions, we need common denominators. That's going to be my first step. And honestly, when you're looking at a problem like this, it looks like such a mess. You might not know what to do, but again, just like that last guideline just said, try something. And since we have 2 fractions being subtracted, like I know how to do that, I just need to get common denominators. So that's why I'm choosing that as my first step here. So let's get common denominators. The first fraction has a cosine, it needs a sine. So I'll say sine of x times cosecant of x over sine of x times cosine of x. So that was just multiplying a sine on top and bottom. The second fraction has sine, but it needs cosine. So we'll multiply cosine of x on top and bottom, and that would give us cosine times cosine, which is actually squared, over cosine times sine. Alright, so I wrote the first one as sine times cosine, and then this one was cosine times sine, but multiplying the order doesn't matter. So we have the same denominator, so let's put these fractions together. So don't lose sight of what you're doing, right? So we got common denominators so that we could put these fractions together. Let's actually do that now. So the first fraction had sine times cosecant, and then we're subtracting cosine squared. All over that denominator, sine times cosine. And we're just working on the left side, so I'm leaving this completely alone. Alright, now it actually seems like we kind of made this problem even more of a mess, so let's see what we can do to start simplifying things. First, I just want to quickly point out that you can't cancel sine and cosine and one of these cosines. It doesn't work that way, and the reason why is because on top, these 2 terms are separated by subtraction. On the bottom, these 2 are separated by multiplication. And of course, this whole fraction is basically like a division problem. And division and multiplication, those 2 things, those undo each other, but like this multiplying and the subtracting, those don't undo each other. So we can't just cancel out a few of these terms like I showed here. Instead, what I'm going to do is just take a look at the numerator. Let's see what we can do there. So I've got sine times cosecant. And like I said earlier, we might want to just change everything into sine and cosine. So this is going to be an opportunity to change cosecant into 1 over sine. So I'll leave that first sine alone, and then this is going to be 1 over sine of x minus cosine squared, all of that over sine times cosine. Again, it seems like we made it even messier, but now I can take this sine, think of it as being over 1, so that all of this cancels out and just leaves me with a 1. So now I have 1 minus cosine squared of x, all over sine times cosine. Alright, so now we're making progress. This seems like it's getting a little bit better now. And actually, 1 minus cosine squared, that's a Pythagorean identity. So I'm going to change that into sine squared. And now that I have just one term on top and sine times cosine on bottom, I can cancel out this sign with one of the signs on top. So I'd be left with just sine over cosine, which is very close, right? Because sine over cosine is tangent. Now I'm going to be kind of picky about this and show that work in a few steps. So I'm actually going to bring this all the way back up here and say that I'm just left with sine of x over cosine of x. Now I'm still just working on the left side, but I started to run out of room, so I'm just doing it up here. So in this step, technically all I did was cancel out those signs, and that's why I wrote this as my next step. And then the last step will say tangent of x equals tangent of x. So now I'm done. And again, it's just kind of nice to end with that little shaded in square just to show like where the end of the proof is. Especially as these proofs start to get longer, it'll be nice to have something very visible so you know where the proof is ending, just like as you're looking through someone's work. Okay, for example number 5, we have secant squared minus 1 over secant squared equals sine squared. Again, we've been working on the left side for all these problems so far, but it is okay to work on the right side. It's just we haven't seen a good example of that yet. In this example, again, the left side is the more complicated thing, so I'm going to work there because I'll follow some steps to simplify it. Like that will help me with the problem. Whereas if I worked on the right side, I just have sine squared, and that doesn't really give me any direction. Like there's nothing to do to simplify it really. Now, there's two different ways that I think about proving this. I'm actually going to show you both of those because it's pretty quick. The first thing I think of is in this fraction, the numerator has two terms in it. So I'm actually going to break this fraction up into secant squared over secant squared minus 1 over secant squared. All right, now secant squared over itself is just 1, and 1 over secant squared, well, secant is the reciprocal of cosine. So this is 1 minus cosine squared. And this is another Pythagorean identity, right? 1 minus cosine squared is sine squared. And sine squared equals sine squared. So that's done. But I actually wouldn't normally do it that way. And the reason why is if you start with this fraction, I know it looks like this complicated fraction, but it's really just one term. And if you start with one term and you're trying to get it to end with just one term, it seems kind of counterintuitive to break it up into two things. In this case, it happened to work, but in most cases, I wouldn't think about breaking it up. I would think of secant squared minus 1 as actually being tangent squared. So again, that's a Pythagorean identity. So we have tangent squared over secant squared, and I'm trying to get it to be sine squared. So this is another instance where we have tangent squared, secant squared, sine squared, just a whole bunch of trig functions. Let's change them all into sine and cosine. Okay, so in this next step, I'm going to change tangent into sine squared over cosine squared, and then I'll draw a bigger fraction bar just to show you that that's just the numerator, and then secant squared is 1 over cosine squared. All right, got a little close here. All right, now we have a fraction divided by a fraction, and of course that's the same thing as multiplying by the reciprocal. So I'll write cosine squared over 1. And now we see that the cosine squares can cancel out, and we're left with just sine squared equals sine squared. And it's totally up to you which one of these methods you would want to use. The one on the right seems like it took a little bit more writing, but it might seem more obvious to someone, whereas the one on the left doesn't really seem so obvious because we're breaking that fraction up, but it didn't require as much work. Number 6 is another example of adding two fractions together. So that's kind of cluing me into my first step. I'm going to get common denominators. So I've got 1 minus sine over here. It needs 1 plus sine. And since these things are separated by addition and subtraction in the bottom, you have to think of them as like one big factor, 1 minus sine. So I'll multiply 1 plus sine on top and bottom. Now these are conjugates, and I know when you multiply conjugates together, you get a nice result. In most cases, I wouldn't multiply these two denominators together, but in this case I will because it will work out nice. So 1 plus sine times 1 minus sine is 1 minus sine squared. And that's nice because that's cosine squared, which might come in handy later. But back to this first step, we also have to change the second fraction to having a 1 minus sine on top and bottom as well. Again, it might be tempting to cancel out a sine with a sine, or maybe just like this whole thing with one of these, but you can't do that. And the reason why is because these two terms on top are separated by subtraction, as well as these on the bottom. But this sign is being squared. So they are very similar looking, but they're not factors themselves that are similar. But don't worry about canceling, because remember the whole point of doing this first step was to get common denominators so that I could add these two fractions together. So let's do that instead. So I've got 1 plus sine, and then over here I've got 1 minus sine. So 1 plus 1 is 2, and the sine and negative sign will actually cancel out. So I'll cross those out. On bottom we still have 1 minus sine squared. Again, that equals that right side, which I'm just leaving completely alone. I'm not going to write anything over there. Now, like I said before, 1 minus sine squared is cosine squared. So let's change that. Let's say 2 over cosine squared. And I think we're getting pretty close. We've got 2 over cosine squared, and we're trying to get 2 secant squared. So it's nice that we have the 2 there. I just have to change this over cosine squared into secant squared. And that's kind of like in the last unit when we were talking about identities. when you were simplifying identities, you always wanted to simplify it down to not having a fraction in your answer if possible. So this is a good example of that. The way I'll do it is I'll think of just like bringing the 2 in front, and then I'd have 1 over cosine squared of x. And of course, 1 over cosine squared is secant squared. And that equals 2 times secant squared of x. So we proved it. Now I wrote those parentheses on the left side, and that's okay. I know it doesn't match up perfectly with the right side, but those parentheses don't really mean anything. If it bothers you, you could write one more step. I'm just going to leave it how it is. We're just going to try 2 more examples, and that will be it for today. In number 7, we have tangent squared plus 1 times cosine squared minus 1 equals negative tangent squared. Again, I'm going to choose to work on the left side because the right side doesn't really give me any direction, but I know I could maybe multiply these 2 factors together, or actually before we even do that, I've got tangent squared plus 1, and I know that's secant squared. So now I have secant squared times cosine squared minus 1. Now this is close to being a Pythagorean identity. It's actually 1 minus cosine squared. That would change into sine squared. So since these don't match up, I'm actually not going to use a Pythagorean identity. If you wanted to, I suppose you could take the cosine squared and just change that into 1 minus sine squared, and then we would still have minus 1. But I'm not sure that that helps us so much because secant and sine are not related. But if you look through your identities, secant squared and cosine squared are related because they're reciprocals of each other. So what if we actually multiply secant squared into these parentheses, like distribute it in? Remember, the reason I said that would be nice is because these are reciprocals of each other. So secant squared is 1 over cosine squared. And I'm also going to write this cosine squared as being over 1 in the same step, because that's not really doing anything, I'm just kind of rewriting it. Again, leave the right side alone. And now these cosines will cancel. So we're left with just 1 minus secant squared. Now the question is, how do we get that to be negative tangent squared? Well, I know that secant squared and tangent squared are related with a Pythagorean identity, so I'm going to start there. Let's just leave the 1 alone, because this doesn't change into tangent squared exactly how it is. So we'll leave the 1 alone, and then minus. Now I'm going to put parentheses around this, because secant squared is actually tangent squared plus 1. Now, if we distribute this negative through, we'd really have 1 minus tangent squared minus 1. Okay, so 1 minus 1, if you combine those like terms, those will just go away, and then that's how we're left with just negative tangent squared equals negative tangent squared. So that one made a lot of use of the Pythagorean identities and the reciprocal identities. Alright, number 8 will be the last example in this video. We have tangent plus cotangent equals secant times cosecant. Once again, I'm actually going to choose to work on the left side. In this problem, one side doesn't really seem more complicated than the other. Like here we're just adding 2 trig functions together, here we're multiplying 2 trig functions together, so they seem about the same difficulty. But the reason I'm choosing to work on the left side is we have tangent plus cotangent. I could change those both into fractions, and like I said, this kind of gives me a direction to go because now we're adding 2 fractions together, and I know I'll need to get common denominators. Also, I know that that's the right move because that would be taking these 2 terms and adding them together into just 1 term, and that's what we have over here. These 2 things being multiplied together, that's just 1 term. So let's do that. In the first fraction, we'll need a sine on top and bottom, and in the second fraction, we'll need a cosine on top and bottom. Again, that was just trying to get the denominators to match up. So over here we've got sine times itself over sine times cosine. And then over here we've got cosine times itself. So cosine squared over sine times cosine. Again, the idea was to add these fractions together, so let's go ahead and do that. We've got sine squared plus cosine squared on the top, and that's looking really nice because sine squared plus cosine squared is a Pythagorean identity. So let's go ahead and make that change because sine squared plus cosine squared is 1. That really simplifies this down. And now we have 1 over sine times cosine. And maybe you recognize that sine is the reciprocal of cosecant, and cosine is the reciprocal of secant. So if I really thought of this as 1 over sine times 1 over cosine, so I just use a little bit of algebra to break these fractions up. And of course that's okay. Think about like multiplying these fractions back together. You would just get 1 over sine times cosine. And like we said, 1 over sine is cosecant, and 1 over cosine is secant. Again, those are in a different order than is written up here, but that doesn't matter. Multiplying in a different order doesn't matter, so it's totally okay to end your proof this way. It's a little sloppy, so if that bothers you and you want to go one step further, that's totally fine, but you don't have to. So there's quite a lot of examples. This should be enough to get you started on your first few trig proofs. Remember to just keep looking back to those guidelines that we went over, and those will help you if you get stuck.